Hello, am I audible? Hello, okay. So, what have we discussed in the last class? Anybody remember? Till what point we have discussed our problem? Okay. What about others? What have we discussed till the last class? Anybody remember? Okay. Let me start. Let me check. Okay. So let's begin our today's session. So, good evening, everyone. Welcome to the NPTEL course of Techniques of Material Characterization of Week 6 of your doubt and problem solving session. So, I think in the last class we were dealing with some questions related to the contrast in TEM. Just let me check with this. Yes, I think yeah, we have I think we have done this question like your modes like dark field, bright field in your TM images. So I think this question till now we have done. Yeah, so let's do some numerical problem. Like I have collected some people asked, maybe it could be in your assignment. Some simple, not very hard. So this is a very good example. It could be asked in any of your examinations because it is regarding your evolved sphere. So the question is asking if the radius of evolved sphere is 300 per nanometer. Okay, so what will be the operating electron wavelength of this instrument? So they have given the radius of the evolved sphere and you have to find the wavelength of electron. Okay, so this you have to find, this you have given. So yeah, So let's do this. Please try to do it by yourself and let me know what is the answer, and I'll check whether it is the right one or the wrong one. Yeah, please do it fast. I'll give you some few minutes. Question is in front of you. Please try doing it. So Arjun has answered 0.0033 nanometer. Okay. Others also please solve and give the answer. Yeah, so only one has answered. Uh, Arjun has written, okay, so 0.0. Sir, in assignment 5, correct option was not available. For question, the radius for which 0039 nanometer is the correct answer. This was not available in the options. Please look into it, sir. Maybe later now we can discuss about. Okay. Okay. Maybe sometimes, guys, it can happen like, but don't worry about it. I mean, they will consider, but definitely, if it is not your problem, then they will consider this. And for the time being, they didn't give you the marks, but it is fine because if you all are getting same answer and that is right, then be with it, and it's not that very. But okay, I'll look into it if something is coming. So okay, those who has not come with the right answer, I'll just explain very quickly and then we'll go ahead. Okay, so that the others can also understand in the video. So this is your evolved sphere, and this is nothing but the um, what it gives. It will give the relationship between the reciprocal lattice and the diffraction pattern, which can be demonstrated rather more formally by the evolved sphere construction. And here the electron beam is represented by a vector of length 1 by lambda. Okay, this is your 1 by lambda parallel to the beam direction. Okay, and the terminating at the origin of the reciprocal lattice. So here the radius will be your 1 by lambda. Okay, it would be drawn, and the condition for diffraction here, what it could be, the diffraction occurs when the evolved sphere touches the reciprocal lattice. Be remembered, it is very important point. The conduction for diffraction is what diffraction occurs only when the evolved sphere, and you see this, touches the reciprocal lattice. Here it is touching the, this is your reciprocal lattice. Okay, so the radius of the evolved sphere is large compared to reciprocal lattice vector, typically about 5 per nanometer. For a small angle of diffraction, the evolved sphere can be considered. So here it is what, sine theta equals to 1 by d by 2 equals to lambda by 2d. Okay, so what they were asking here, they have given the radius. Okay, radius they have given. Okay, so and what they are asking, they are asking the wavelength lambda, they are asking. Okay, so it is nothing but this is very simple. So here the radius is already you have given radius, which is 300. So 1 by 300 is what, 0.0033, and sometimes it can ask theta also, so like that. But yeah, the question is you can take the range 0.0.003334 like that. So all are right. Okay. Okay, yeah. So let's go ahead. Let me connect my laptop with charger. Yeah. So as per structure factor, forbidden reflection for an FCC crystal is what? Yeah. Tell me, what is forbidden crystal? Sorry, forbidden reflection for FCC. 100. Okay. So let's see. So, bulk diffraction selection rules for common conventional unit cells are what? This is, you have to remember this. Okay. So when you have a primitive unit cell type, so what is the allowed reflection and what is the forbidden reflection? So when, sorry, for primitive any HKL and forbidden reflection is none. Body centered allowed reflection is H plus K plus L should be even, and here H plus K plus L should be odd. For face centered, H, K, L all odd or all even, and here HKL could be mixed one, mixed, odd and even for forbidden. FCC diamond, HKL all odd, HKL all even, and H plus K plus L. If it is even, then it could be 4n, or it could be a, for forbidden reflection, S plus HKL mixed odd even and HKL all even, then S plus K plus L is not equal to 4n. For HCP, L even, S plus 2k is not equal to 3n, L is odd, S plus 2k equals to 3n. So these are some basic that you have to remember for the allowed reflection, for the forbidden reflection. So here in the question it is not for the allowed, it is for the forbidden reflection. So it is asking FCC. So for FCC is what? HKL mixed odd even. So here 1 is odd, 0 0 is even, 2 0 0 all even, 1 1 1 all odd, 2 2 0 all even. So the only option is left is 1 0 0. Understood? And these are regarding that. You just go through this slide, you will understand that about this is given structure factor and Bragg law together decides the nature of the diffracted beam. So these are nothing but how they have decided like this. So allowed reflection in the FCC crystal structure and their interplanar spacing. Okay, this is for FCC. Allowed, like you can see 1 1 1 2 0 0 2 2 0 3 1 1. Yeah, the answer was 1 0 0. Now, for a high energy electron beam, the radius of the evolved sphere and diffraction angle respectively are what? Just now we have developed, or I have shown the relation. You can guess it very quickly. Yeah. So A, large and small. Okay. Yeah. So this is what the radius of the evolved sphere and diffraction angle. The radius is this, and diffraction angle is theta. So watch here. When your radius will increase, your diffraction angle will decrease. So it is large and small. Okay, when your radius will increase here, your diffraction angle will decrease. More the radius, see here, more the radius, so less will be, small will be your diffraction angle. So yeah, you are right, large and small. Burgers vector of dislocation can be determined in TEM image by what? SAD pattern, bright field imaging, appropriate zone axis selection, HAADF mode of imaging. So it is regarding, just remember, for Berger vector can be determined in TM. Okay, or you can say like that, which one is the appropriate in TM for the determining your Berger vector of dislocation. Yes. What is the answer? C, D. Okay. So one is saying appropriate zone axis selection or HADFT. Let's see. So just a second. Yeah. So the dislocations are invisible or exhibit only weak contrast is giving. Okay. This is the magnitude of your Berger vector, and certain planes near a dislocations are bent and the bending decreases, increasing the distance from the, yeah. So here you can see, okay, from the dislocations, if these planes are bent into a strongly diffracting orientation, the intensity of the directly transmitted beam will be reduced and that of the diffracted beam increased in columns near dislocations. Okay, so the dislocation will appear as a dark in the BF or the bright field image, or as a bright line in the dark field image. So this is your like a diffraction line, and this is your this is incident, this is your transmitted, and this is your transmitted, this is your diffracted. Okay, so planes near an edge dislocation bend into the orientation for diffraction. Okay, so here this is your example of dislocations. So here you can see how this is moving. Yeah, this is like a dislocation, perfect image of dislocations. So diffraction contrast can be used for Berger vector determination by different diffraction vectors. So here you can approximate zone size selection. Okay, so this is mainly used for the zone size selection, because here also you can see it is mainly can be this diffraction contrast is they are using for the Berger vector determination by different diffraction vectors. Okay, so suppose this is the direction 1 bar 1 1, so this is one axis, and here when it is moving 1 bar 1 1, so they are defining that in which direction you are when your Berger vector is in that direction. So it is easy to define your that in which direction your zonal axis is there. Okay, so through Berger vector it is possible that your uh, appropriate zonal axis can be selected from.
Sir, also bright field imaging is for the this location now, sir.
Bright field, what you are asking?
So bright field also here in the theory
Huh?
at the beginning there is a for the this location line. If the bright field we can go for the bright field, then it this location line in the
No,
dark
no, no, no,
in the
no.
dark field.
It is saying this line here you can see it is just it is asking about that what it can be determined. Okay, it is not
Yes.
saying about bright field or dark field. Here this is the addition
This,
your
this also this is
information.
determined, sir, in the bright field image. If we go to the bright field image, then this location will appear in dark as a dark line.
Yes,
And for the bright field line, it will go to the dark field image.
yes, I cannot
Yes.
understand your question. Can you repeat?
No, in this question, this may not, sir, answer this bright field image. So at the
Here you are not determining bright field image. Here you are using a bright field image to determining the zonal axis. There is a difference. You are not using the Berger vector of dislocation to determining the bright field. Okay, you are using bright field imaging to determine the
sir,
Berger vector.
how we can this question? How we can go this question answer is approximate zone axis selection, because at the in the theory there is no any I mean theory that they say that the approximate zone axis selection is applicable for determining this location. Sir.
See, as per my what I have just see that if it is not given in the lecture, then try to read some more book. Maybe from there you can gather some knowledge. But this is you can see like this is a different in the different orientations. So in the different direction, the magnitude of your Berger vector is different. Okay, so if this is changing, then through this direction you can determine that where your zonal axis could be possible. Understood? Because here, suppose if your dislocation is in this direction, so here it is like this. Suppose you can see here, this is like a dislocation. So here it is 1 bar 1 1. Here it is different. Here it is different. Okay, maybe I'm not very expert to select this. For this you have this TM imaging and all. You need a very good skills and all to understand that where your planes are and how uh, uh, the things are changing in the image. It's not that something you will just see and you can catch. But yeah, from there, from this point of view, as a conclusion, I can say that yeah, from this direction where your Berger vectors are moving, in which direction it is located. From there you can something you can give which is related to axis information. So yeah, zonal axis could be possibly one of the main. And you are saying about the bright field. So bright field, it is not giving the bright field, it is giving in the bright field imaging mode the information regarding the zonal axis. Okay, by using a bright field as well as dark field also. Here you can just see the dislocation will appear as a dark line in the bright
Yeah,
field
yeah,
image
yeah.
or as a bright line in a dark field image. So you can use dark field also, you can use bright field also. It is just a
Yes,
matter.
sir. So in the option bright field is there, no sir. Dark field is not there.
Yes.
So its answer is not bright field, sir. Maybe.
No, no, no. Actually, you are not understanding the question. Question is asking about what it could be determined. Just try to understand. It is not asking by which mode or which imaging you are using. Here you are using bright field either or either dark field to determine. You are not determining the bright field. You are using, you are determining is yet something you have given, something you are using, and you are determining something else. I mean something is input or something is your environment, and on that presence of that you are try to get something information from there. Okay, so bright field imaging is something that you are using as a mode, right? Or dark field also you can use just to determine the Berger vector of dislocation. Okay, so that Berger vector of dislocation you will can determine in the bright field imaging, and that will give you the information about the zone axis selection, because it is mainly giving you some information or some output which is regarding your direction. Okay, so this is regarding that. So zone axis is the right answer. I hope it is clear. So yeah, let's go to this. Intensity in a SAD pattern is related to what?
Structure factor, sir.
Okay. Others also. D. Okay. So yes, you are right. Structure factor. So here it is regarding that mathematical distinction how materials scatter incident radiation. So this is your each type of plane in a crystal will have a different spacing and a different density of atoms per unit area, and how we may expect that the intensity of electron diffraction will be different from each type of atomic plane. Okay, so it is obtained by adding up the contribution to electron scattering made by each atom on a given plane, taking into account the phase of each wave that is scattered. Okay, so here you can see this is your structure factor, and this is real space. It is given. Yeah, so this is like a real space, direct space. This is your crystal, and when it is a Fourier transform, it looks something like this in a reciprocal lattice. Okay, so and this is also a crystal, and this is your Fourier transform. This is your electron density, and when you will do the Fourier transform, it will give you the structure factor, which is given by this HKL. So I will also see maybe it is not giving something. Yeah, but the SAD pattern is here. Yes. So maybe I think I have to. I forgot to add one more slide was there. So I will add. But yeah, the structure factor was the right answer, because the SAD structure factor is what? It is the Fourier transform. Fourier transformation. If you have like in the mathematics, maybe you have must be studied this, like how this Fourier transformation occurs. So this is the electron density, and when you will Fourier transform, it will give you the structure factor. So this is mainly occur by using your SAT pattern. Okay. Yeah. So the images produced through SEM are what? Direct, sequential, both, same as TM. It is very simple. So Arjun is saying B. Yes. So in SEM is what? A type of electron microscope that produces images of a sample by scanning the surface with a focused beam of electrons. The electrons interact with atoms in the sample, producing various signals that contain information about the surface topography and composition of the sample. The electron beam is scanned in a raster scan pattern, and the position of the beam is combined with the intensity of the detected signal to produce an image. So yeah, this is a sequential. It's not something. It will give you the direct. It scan like a raster scan manner in the XY direction. Okay, so it is like a sequential scanning. Okay, and this is the SCM image. You can clearly see how beautiful this is looking. Different morphologies. So sequential was the answer. It is not direct. What is the main purpose of using scanning mode in SCM? Decrease the field of view for better resolution and increase the field of view. No such specific purpose. Yeah, what? C. So Arjun is saying to achieve better resolution and better increase the field of view. So yeah, C is the right answer. Let's see how. So resolution is how. So here you will see in older instrument the fine beam of electron is scanned across the specimen by scan coils while a detector counts the number of low energy other radiations and each point of surface. So here it is giving like this. The raster scan on the specimen. So cathode ray tube is scanned across the screen while the brightness of the spot is modulated by the amplified current from the detector. The electron beam and the CRT cathode ray tube are both scanned in a similar way, that is in a rectangular set of a straight line known as a yeah, this is like a rectangular and it will scan like this, going like this, then coming, then again going in the xy direction. So it is like it is called a raster scan. So this electron, yeah. So in modern instrument, the same effect is achieved by digitally controlling the beam position on a sample, resulting image displayed digital space. So it will be giving this kind of a image. It will give a, this is like a point to point or in a very in this way it will give you the image, and at last after the raster scan you will get a whole image point to point. So here you can see uh, the raster scanned by the electron beam on the specimen is smaller than the raster displayed on the CRT. Yeah, in the electron beam on the specimen is very small. Okay, what you see in the digital split. So it gives a very good and the magnified image or the resolved image. The linear magnification side length of the CRT divided by the side length of the raster of the specimen. This is giving them some mathematical. For example, if the electron beam is made to scan a raster of 10 micrometer by 10 micrometer on the specimen, okay, it is scanning suppose 10 by 10, and the image is displayed on a CRT screen or digital by 100 mm. Okay, so it is giving you the 100 mm by 100 mm in the screen. So the linear magnification will be what? 10,000x. Okay, because it is scanning your 10 micrometer by 10 micrometer on a specimen, but in the screen or in the display it will give you the 100 mm by 100 mm. So that's why it is a magnification of how much? 10,000x. Okay, so it is giving you a better resolution. Main the scanning mode is what raster scan. The it will give you the again and again scanning. It is giving you the better field of view. You can see it very magnified version, and also with a more resolved images you can find by using a scanning mode. So that's why it is saying how scanning mode works. It is regarding that. The secondary electrons are what? Low energy, formed by inelastic, formed by elastic, high energy formed by inelastic, or formed by elastic. A. Option A. Low energy formed by inelastic. Yes. So here it is very simple. Secondary electron is what? It is coming from a very near to the surface. Okay, this is your secondary electron Se1, Se2, Se3. So here they are also likely to be electrons to which a small amount of energy has been transferred within a short distance of the surface. And this is not a very accurate term, but it is used to those electrons which escape from the specimen with energy below about 50 electron volt. So it is less than 50 electron volt, less than. And also it is what? It is inelastic. Why inelastic? Because it is some small amount of energy has been transferred. So it cannot be elastic, because in elastic there is no transfer of energy, but here it is transferring the energy. That's why the low energy and the inelastic. So the right answer is A. Now phonon scattering is important for what? Elastically scattered electron, backscattered, secondary, both. A. Yeah. So phonon scattering. Phonons are the quanta of elastic waves. Okay, that is caused by the atomic vibration in a solid. The amount of energy lost in phonon scattering is rather small, less than 1 electron volt, and the mean free path for high energy electrons is quite large, for the order of micrometer. Okay, so here you can see how it is. Short wavelength phonon, this is, and this is your hot electron, the red one, and this is your mid long wavelength photon, and this is your cold electron. the phonon scattering is important for two main reasons. All electrons which remain in the solid are likely to excite phonons eventually, and this is how the solid is heated by the electron beam. And when phonon scattering occurs, the scattered electron is generally deflected through quite a large angle, typically 10 degree. This is important especially for secondary electrons. So yeah, so this is important for what? Elastically scattered electron. Here it is saying na, the scattered electron, phonon scattering occurs, the scattering electron is generally diffracted through a quite a large angle. This is important especially for the secondary electron generation. So when there is no phonon scattering, then it can't be. This I will explain when I will explain you that how the electrons are generating from a like different uh, depths, like a secondary electron and that. So why this is important? So for the time being, it is important for the secondary electron to be the phonon scattering. Okay, so elastically scattered electron. Yeah. So the answer is C, secondary electron. Okay, phonon scattering is important for what? Secondary electron generation. Okay, because it will lose some energy, and all electrons which remain in the solid are likely to excite phonons, and this is how the solid is heated by the electron beam, and it will give you some energy to the specimen so that the secondary electron can be generated. Now, what are the chances of an electron to cause inner electron excitation if it has very high velocity? Yes. A. So let's see. So The question is, what are the chances of an electron to cause inner electron excitation if it has a very high velocity? Okay, so when the velocity is high, then the chances of the electron is definitely would be high. A rare but valuable from inelastic scattering is the knocking out of inner cell electron. Okay, so when the binding energy of this is like your K shell, L shell, M, and electrons are high, the energy lost by the primary electron can be quite large in this process. It takes 283 electron volt to remove carbon electron and from K carbon from K shell electron, and 69,508 electron volt to knock out the tungsten K cell, and 1100 electron volt to excite a copper L electron. So the mean free path of this type of inelastic scattering is quite large, so the process occurs much less frequently than plasmon scattering. Okay, now the secondary effect produced when the excited atom relax are almost ideal for analysis. The interaction cross sectional for inner cell excitation is common with that most scattering process drops as the primary electron energy increases, and it is also lower for the elements of high atomic number. Okay, which is increases with the jet. So here it is mainly saying, the question was the chances of an electron to cause inner electron excitation if electron has a very high velocity. So when the electron is coming from a very high velocity, it will knock off the inner cell electron because it has the energy. Okay, it is coming from the high velocity, so it is more likely that it can knock out the inner cell electron, so the chances is increasing. Okay, sorry, oh just a second, you said increasing. Yeah, sorry, it is different. It is saying that the mean free path for this type of inelastic scattering is quite large. Okay, sorry, I misunderstood. So here it is saying that suppose let me how explain in this way. Yeah, so let's say the interaction cross section for inner cell excitation, okay, so drops as the primary electron energy increases. So if it is coming from a very high velocity, it means it is having a very high energy increase. So the interaction, because it is coming from a very high velocity and since it has a high energy, the interaction cross section for inner cell excitation is drops or is reduced in common with that of the most scattering. So in the most scattering, what is happening? So if the velocity is less, it can interact more. Okay, but if it is coming from very high velocity, sometimes it can interact, sometimes it cannot interact. Okay, but if it has a low velocity, it can interact to some atoms and it can go and knock out the electron from the inner cell, but it is coming from a very high velocity since it has a high energy, so that's why the drops at the primary electron energy increases. Okay, so mainly it reduce. Now it is very good question. The graphite electrode are being used in lithium ion batteries. Okay, it is very well known. And which method will be most relevant for studies the degradation of such batteries? Okay, how you will determine that your battery is degrading? By characteristic X-ray, by characteristic X-ray and Auger electron, and there is no such method. Yeah, how you will determine your battery is decreasing, degrading? So yeah, the obtaining a signal in SEM, the region into which the electrons penetrate the specimen is known as the interaction volume, and throughout it various radiations are generated. So the primary electrons loss energy, the amount of the typical the secondary radiations will alter. Even though radiation is generated within this volume, it will not be detected unless it is escapes from the specimen, and this is will depend on the radiation specimen. The volume of material contributing to the detected signals is the sampling volume. Okay, so this is a different signal is generating. So here you can see the Auger electron generation. So here these are like, this is the process how the Auger electron is generating. Okay, so this you can read from there, that how the electrons are coming and knocking out the electrons, and this the knocked out electron will interact, and the electron from the high energy cell will come to fulfill the that place. So here the three electrons are now involved: the original vacancy, outer electron which jumps into, and the other outer electron which leaves the carrying out surplus energy. So an alternative here, X-ray emission is the ejection of outer electron carrying the excess energy as kinetic energy. Okay, so here these are something that is coming. So the measurement of energy of characteristic Auger electrons from the basic of Auger electron spectroscopy is this. So here the main, the Auger electron spectroscopy is what? This is mainly give you the information regarding whether, because it is giving you the surface information. So from the surface, if your battery is degrading, then there could be some changes in your surface, and that can be obtained from your Auger electron microscopy. You don't need to go to the very high depth. Okay, so that's why you can use a Auger electron spectroscopy, and this is how the process that is coming your Auger electrons. This is your high speed electron knock out the inner cell electron from an atom. Okay, now the vacancy creates. Now upper cell electron will come and fill this vacancy. So in this process, what will happen? Auger electron will emit. This is your Auger electron, and the X-ray photon emit. Okay, because when this is coming, the X-ray will come because of the energy difference between these two cells. Since for heavy atoms the energy is in the range of X-ray, it is called the X-ray fluorescence. But sometimes the energy is emitted is transferred to the outer electron, ejecting it from the atom. So this is the Auger electron. This is how Auger electron comes. So Auger electron is the main.